All right, so to begin this second session just before we break for lunch, the second session is going to introduce this method called the Laplace approximation and try to go through a class of models or show circumstances where it seems like a good thing to do. And all of that leads up to, or is sort of shown within the framework of this package called INLA, which stands for the Integrated Nested Laplace Approximation, which we'll be able to run some model fitting examples with by the end of this portion of lectures, so after lunch. And I think what you'll enjoy about INLA is that although it is only designed, is deliberately only designed for a very specific class of models, the class of models which it allows you to fit are models which do contain Gaussian processes. So it gives you a very sort of a user-friendly and computationally quick way in order to get into trying out some Gaussian process models and seeing, getting a feel for the way that they work. So a very low-cost approximation for moments of the posterior and marginal densities. By moments, I mean, for example, the mean or the variance of the posterior. A very low-cost approximation for these is provided by this thing called the Laplace approximation, which literally does date back to Laplace. So the circumstance is this, just outside of probability theory, just in general, if we're trying to integrate some kind of smooth, well-behaved function, f, taking parameters x, like below, one way to approximate that integral is to examine the second-order Taylor expansion to the logarithm of that function about its maximum, and that's the maximum in the log space. And it looks like on the right. So we have our original function on the left and our log function on the right. We find the maximum, and which, computationally is probably quite efficient just by an optimization step or an optimization routine, and if you have gradients, probably even quicker. So we're going to use the second order Taylor expansion, which would look something like this. So we have our function is obviously the exponential of the log of the function that follows, and we're going to approximate it by the exponential of our Taylor series expansion about the mode of the function, about the mode, and the Taylor expansion is going to be in the logarithm of the function. It looks like that. So it takes a term which is constant out the front. Am I on here? Yeah. So it takes a term which is going to be constant. It depends only on the position, which is the position of the maximum, which is fixed and found. And then it adds this term, which is the second order derivative of the log of the function evaluated at the mode. And then it will be taking, because it's a second order Taylor, it'll be taking a squared term. I've dropped a constant term, which doesn't matter. So this approximation, we can bring a constant out the front. And now what we're going to do is look at the remaining term, which we want to integrate. This looks to us, if we're familiar with Gaussian or sort of a normal densities or Gaussian distributions, this looks like something we recognize. It's a constant, or it's inside the exponential. It's a constant multiplied by a squared term with an offset about x naught. And so we can write down this result using the normalization term, which we know from, which we know as the normalization of our normal densities, or which we could derive from other methods using these techniques for exponential integrals. But the simplest way to see it is to just compare this expression, which is like the Gaussian, which is like the normal density unnormalized, and say, well, if we're going to integrate from negative to infinity over that, we must get something which was the normalization constant of the normal. So that's kind of a cheating way to get that result. We can apply the Laplace approximation in a few different contexts. One of them is to approximate marginal likelihoods, in which case we would look at the unnormalized posterior and we'd look at that integral. It's not a great approximation to most marginal likelihoods because oftentimes the posterior will have some kind of non-normality about it. It would be a little bit skewed, a little bit, maybe have fatter tails than the normal or some other behavior. So I wouldn't recommend the Laplace approximation as a sort of a go-to technique for marginal likelihood estimation when you're trying to compare, say, just two models and you're working in the context of, deciding between two cosmological models from your expensive cosmological probe. That said, it's an approximation which for many models will improve as more data is added. So as the posterior moves towards normality, it can improve. We can also use it to approximate various other functionals of the posterior. So by functional, I mean if you take the posterior and you want to know what is the expectation for some function of the parameters with respect to the posterior, it's an integral of that function against the posterior density. We can do this by applying two Laplace approximations, one on the numerator and one on the denominator. And these tend to be a little more accurate in general because it's sort of like we're balancing the errors from our normalization or of our approximation up the top by the errors of our approximation at the bottom, and it tends to have a faster convergence than the original marginal likelihood estimate. So that was the case for a univariate parameter. When the parameter space is multidimensional, what do? We simply replace this term, which is the negative second derivative of the log of the function, with the negative of the determinant of the Hessian matrix. So if you know the Hessian matrix, it's like the matrix composed of all possible permutations permutations and combinations of these of the indices. So it's along the diagonal, it's all of the second order terms in a single variable, and on the off diagonal, it's all of their mixtures. And so for a well-behaved sort of unimodal density like this in 2 dimensions, it'll be a 2-dimensional matrix which we can take the determinant of. So that's the extension to higher dimensions. Obviously, the Laplace approximation is going to perform best when the function we're trying to integrate is as close as possible to a Gaussian distribution or to a multivariate normal. So if it was exactly a multivariate normal, then we'd be working in the regime where the Laplace approximation is the exact solution. So something like this, like fantastic, we're definitely going to do very well with the Laplace approximation. If our posterior or whatever the function we're trying to approximate starts to become highly multimodal or the two of the parameters are rather degenerate and you get this type of shape, it's not going to work as well. We're effectively plonking down a big Gaussian over this and in fact over one of these peaks, whichever is the greatest, and we'll be losing a lot of the mass of this distribution. So we for sure won't do as well. So this is the regime where we're doing poorly. Nevertheless, we are lucky because for a wide class of Bayesian models, there's a theorem called the Bernstein-von Mises theorem, which shows that asymptotically, in terms of as the amount of data increases, the posterior will tend to converge towards normality. It's sort of like you could imagine this as a central limit theorem for the posterior. Well, that would be sort of an improper way to say it, but that's the effect, is that for simple models, for models in which we're not like adding new parameters or increasing the model complexity as the data grows, for models in which the model complexity is fixed and the data increases independently of the model complexity, then these ones, for the most part, will converge towards normality. So those type of models, so well-behaved models, are going to be a good thing to look at for the Laplace approximation. And there's another way that we can help ourselves out, which is by choosing normal priors. So if we put a normal prior on the parameters we're going to put a Laplace approximation on, then we already give ourselves a little bit of a sort of a nudge in the right direction for this to be a reasonable method of approximation. So one place where these conditions can occur is for hierarchical models featuring latent Gaussian random fields. And this is indeed the type of modeling situation which I was describing earlier for the malaria data. Technically, when we're talking about increasing data volumes here, I mean for increasing data at a fixed number of sites. If I would be imagining a scenario where we have an increasing data set, but it's just adding more and more sites, that's not the type of convergence I want. I want that we're adding more data from each site, so that would be a technicality. But the most important thing, I suppose, is to see that these latent variables which are added via the Gaussian process sit very close to the top of this hierarchy, so they're very strongly informed by the data which we do have at the sites. So that's going to be important for getting this type of Bernstein-von Mises convergence towards a normal posterior. And then the other aspect is that we're dealing with a Gaussian process, so the Gaussian process itself defines a multivariate normal prior over those latent variables. I'll explain a little bit more of that later. So effectively, well, all that to say, there are a large class of models, these ones with latent Gaussian processes lying close to the top of the likelihood function, which do have a reasonable chance of being well approximated by a Laplace approximation. So this is more or less the intuition behind this integrated nested Laplace approximation software. What it does, the INLA package, is to implement a modified or improved Laplace approximation to integrate out near normally distributed random effects, so ones like this, which come from a Gaussian process usually, and that's for the latent variables. And then for any remaining parameters, so parameters controlling things like the slope or the hyperparameters of the Gaussian process, we're not going to do MCMC sampling, we're going to do a grid-based search. So it generally finds the optimum point and then places some grid points down. It's somewhat counterintuitive in this day and age where MCMC methods have really become the go-to for statistical computing, but it's the case that in very low dimensions, it's really difficult to do better than an approximation method based on a well-placed grid. So a grid which is well-spaced and well-centered, which I guess is one of the tricks of the INLA software in designing such a grid. But where dimensionality is low, this type of strategy provides you in some sense, a cheaper approximation than one which is based on randomly moving about the space. So we'll later on use the INLA package to do some exploratory data analysis. But after lunch, I'll introduce the type of models that we can fit with INLA and specifically explain just what are Gaussian processes in some more detail and hopefully give some insight, therefore, into what kind of astronomical models we might realistically see Gaussian processes emerging in and being useful for. So I think it's lunchtime now, and Guillaume.
Okay, excellent. Please thank Ewan again.